Okay, and then once we get done with all that stuff and we have exam 1, we can go on to electronics. Right, you get 2 8.5 by 11 sheets of notes. If you want to print out those key slides and put them on your note to have them available for you, go ahead and do that. I'm not going to put the tables and all that stuff on the exam. It's just extra paper. But you can put anything you want on there. You can print things out. I prefer not to see things in my handwriting. My own solutions tends to upset me. The only thing that's really ever upset me when I found on people's note sheets is one semester I found 9 people who had the solution to that exam on their note sheet. They all got zeros. Okay. One of them argued with me all summer long on that too. We're down here, we're at the part 2, the inverse Laplace transform. We'll look at some simple examples. We will look at how to deal with partial fraction expansions. That's going to be most of this class. And talk about a few strange things. These are the tables. You can print these out and put these on your exam note sheet. You just print them and make them smaller and it works. Remember, if you want to take the Laplace transform of a constant, it's the same thing as taking the Laplace transform of a step response. Because in the interval from 0, when you're doing the integral from 0 to t equals infinity, u of t is always 1. Okay. More transform pairs. Everything you're going to see on an exam or on the homework will be in one of these 2 tables. There's some properties that sometimes help you out or not. When you take EE280 I know I wrote the course, you will look at it, you will use Laplace transforms again, but it will be more along the vein of using Laplace transforms to solve differential equations. And you get a preview of that in lab 3. Taking derivatives is just like multiplying by s. I do have to include the initial condition though. Second derivative, I multiply by s squared. I need the initial condition and the initial condition on the derivative, etc. When I'm integrating, I'm just dividing by s. Yeah. And so we've been talking about this variable called s. And I just said, probably yesterday, I said it's just j omega, don't worry about it. It's a little bit more than j omega. When we solve differential equations, the general way of doing this is you assume the form of the solution, and the form of the solution generally looks like this, a e to the st. You just assume that's the solution, and then you plug that into the equations and solve the algebraic equations. That's kind of what you're doing with these Laplace transforms. The math turns out amazingly the same. S is a complex frequency. It's got a real part we call sigma, and an imaginary part we call j omega. Omega is like the omega in your cosine omega t. It's a radians per second. The imaginary part, you remember Euler's form or not very well. Like if you're like me, you probably just groaned when I said that. If you have anything that looks like e to the j omega t, those can get transformed into sines and cosines. It's another form of sine and cosine. So if I look at this axis right here, if I'm on the j omega axis, the sigma part equals 0. What I'm seeing here is things that look like sinusoids, depending upon whether it's plus e to the plus j omega t or e to the minus j omega t. If I'm at the origin, both sigma and j omega equals 0. So you have e to the 0t, and that's just a constant. So you've got a DC signal here. You've got sinusoids. Now, if I add this sigma in and give it my frequency a real part, e to the positive sigma t, if sigma is a positive number, I get an exponential that's growing. Generally, engineers hate that because it leads to things blowing up. It's bad. It's bad news all around. It's not stable. If I have a negative real part, if my sigma is negative, I have an e to the negative sigma t, then I have a decaying exponential. That's a good thing. It's something that will stabilize with time. I can combine sines and cosines to get damped sines and cosines. If sigma is negative, like over here, what happens with time is I get a sinusoid, but its magnitude is diminishing with time. It's like there's an exponential envelope on there that's causing it to decay down. And that has both, these A, C, G, and H have both a real and imaginary part. And of course, I have trouble over here because it's a growing exponential. Eventually, it's going to burn something out. So having this complex frequency gives us one form of mathematical signal that I can use to describe a whole bunch of different types of signals. And then you get out in the real world and nothing looks pretty like this. Okay. Special case. Inverse Laplace transform. We talked about that last class. I'm not going to do that again. Other than to say that we talked about this the last class. Sometimes it shows up on exams and people say they didn't know it. Put it on your note sheet. Okay. We want to find inverse Laplace transforms. So I've got some f of s. It's got a numerator that's a function of s and a denominator that's a function of s. In order to find the inverse Laplace transform, the degree of n must be less than the degree of d, which means the highest power of s is the degree. So in the numerator here, the highest power of s I get is s cubed. So it has a degree of 3. And the denominator has when I multiply it out, I'm going to have a 1, 2, we have an s to the 4th term in there. So this has a degree of 4. The numerator's degree is less than the denominator's. I can find the Laplace transform. Now, if they're equal, like in this case, and I put this problem, I put this problem on a 325 exam. Best student in the class just told me it was impossible. And I go, no, Earl. I actually tripped on a problem. I was excited. Okay, you can take this and algebraically manipulate it to get something that's transferable. And let's do this. What I need to do is I need to take 3s plus 2, and I need to find something, some factor that includes s plus 5. So to take care of all the s's, I need to put a 3 out front. So this is 3s plus 15. I've added 15 to this expression. I have to subtract 15 plus 2 over s plus 5. Okay, so now I'm breaking it up into 2 fractions. Before I can cancel, I have to be able to do that. I've got 3s plus 5 over s plus 5. And I've got minus 13 over s plus 5. This fraction I can cancel. I couldn't cancel if it was all over the same denominator. So this is going to be 3 minus 13 over s plus 5. I can take the Laplace transform of that, because the Laplace transform of 3 is going to be, inverse Laplace transform of 3 is going to be delta t.
Why'd you do that negative and plus 2 again?
The negative and the positive right here. I wanted to get this in a form where I could cancel out the s plus 5 over the s plus 5. So I'm just kind of factoring this out so I can get a term that has 3s plus 5 to cancel the s in the numerator. I haven't done that in here in a long, I don't think I've ever done that in here, but I have put that on a 325 exam.
So kind of like completing the square.
Yeah, we'll get to that today too. When I was teaching Algebra 1, where we got to completing the square was like the last week of class before school got out. And so nobody wanted to learn how to do it. So I assume you don't know how to do it. Yeah, I didn't even want to do it at that point. I was ready for break. Okay, so we want to find the inverse Laplace transforms. These terms are already broken down. I look at my table and u of t transforms to 1 over s. Wow, I remember some of these. E to the minus alpha t transforms into 1 over s plus a. Oh, I'm going to have alpha. I'm going to have to look at my table for the next one. It's either a sine or a cosine. It is right here. Sine omega t transforms into omega over s squared plus omega squared. Okay, so that's all I need to know for that one. 1 over s is going to become u of t. So this is 3. And I'm going to leave the u of t off now because I'm going to pull up another rotten trick on you guys. Minus 5 and s plus 1 is going to be e to the minus 1t. Oh no. Slide 13. I'll be back.